Imagine you're staring at a screen right now.
Right.
You're in this remote field office or, maybe a freezing server room,
Okay.
and you've got a user just breathing down your neck.
Oh, we've all been there.
Yeah, it's the worst. And the Wi-Fi icon in the corner of the taskbar is, like, completely full.
Solid.
Exactly. Or maybe the Ethernet cable is physically plugged into the machine. You look down, you see a solid green link light and that frantically blinking amber activity light.
Meaning data is supposedly moving.
Right. So everything on the graphical user interface is screaming at you, we are connected, we are online.
But then you open a web browser.
Yes, you type in a URL and you're just hit with this stark, unforgiving, server not found error.
It's infuriating.
It really is. I mean, the operating system is just flat out lying to you.
Well, it's arguably the most common and definitely the most frustrating paradox in network troubleshooting.
Oh, for sure.
You're basically trapped in this state where the physical layer and the presentation layer of the machine they're telling two completely different stories.
Yeah, totally disconnected realities.
Exactly. And if you rely strictly on those graphical indicators, those friendly little icons that UI designers built, just to keep end users calm.
You will be stuck in that server room forever.
Forever. Because the graphical user interface is essentially just a smoothed over interpretation of reality.
Right.
When it breaks down, you have to bypass the interpretation. You have to interrogate the system directly.
Which is exactly our mission on this deep dive.
Let's do it.
Today, we are taking this massive stack of IT certification material, specifically focusing on advanced network troubleshooting and remote access architecture. And, well, we're tearing open the command line to find the truth.
It's the only way.
Okay, let's unpack this. We aren't going to just talk about, what commands to type. I mean, if you're listening to this, you likely already know your way around a terminal.
Sure, you've opened command prompt before.
Right. So we're going to deconstruct the exact packet-level mechanics of these diagnostic tools. We're going to trace a connection from the local network interface card all the way to a remote server.
The whole journey.
Yeah. And then explore how to securely commandeer those distant machines without, leaving a backdoor wide open for literally every botnet on the internet.
And that is really the core of modern systems administration.
Mm-hmm.
Because when the abstraction layers fail, you kind of have to become the packet.
I love that. Become the packet.
You have to. You have to understand the underlying logic, the causality, and the exact mechanisms of the TCP/IP suite.
Right, because just knowing how to run a command is, it's entry level.
Exactly. Knowing why that command returned a specific error code and what that error code implies about a router like 3 hops away.
That's the real skill.
That's what separates a help desk technician from a network engineer. In a world that entirely relies on connectivity, knowing how to trace these digital paths it's basically the modern equivalent of knowing how to change a tire or read a map.
Totally. So let's start right at that lying Wi-Fi icon.
The culprit.
The culprit, yeah. The limited connectivity versus no internet access states. The Windows operating system uses a specific mechanism to determine what icon to show you.
Right, it doesn't just guess.
Yeah, it uses something called Network Connectivity Status Indicator, or NCSI.
Yeah, so NCSI is this active probing mechanism.
Okay.
When your network interface comes up, the OS doesn't just, assume the internet is magically there because a cable is plugged in.
That'd be too easy.
Right. Windows actively tries to reach out to a very specific Microsoft text file.
Oh, wait, a literal text file.
A literal text file hosted on a high availability server. It sends an HTTP GTT request to something like www.msftconnecttest.com, connecttest.txt.
Wow, okay.
And if it can reach that file, download it, and actually verify the text inside, it says Microsoft Connect Test.
Then the OS flips the switch.
Exactly. You get the clear Wi-Fi icon. It is definitively proven end-to-end internet connectivity.
But, okay, what if that probe fails?
Well, then you get the yellow triangle.
The dreaded yellow triangle.
The dreaded limited connectivity or no internet access.
Mm.
But here's the catch. The failure of that NCSI probe doesn't tell you where the failure occurred.
Right, it's just a binary yes or no.
Exactly. Did the DNS lookup for msftconnecttest.com fail? Was the HTTP packet dropped at your local firewall?
Or did your machine just fail to get an IP address altogether?
Right. The GUI doesn't know any of that. It just knows the text file didn't arrive.
The system tray icon is basically like a car's check engine light.
That is a perfect analogy.
Right. It tells you something is wrong, but you need the diagnostic code reader to actually fix it.
Yep.
So to find out where the chain broke, we have to establish our local identity. We open the command prompt, completely bypass the GUI, and invoke ipconfig.
The classic.
But we aren't just looking at the default output. The real diagnostic power comes when we append the all switch.
Ipconfig all.
Exactly.
Yeah.
Because we aren't just looking for an IP address, we are looking at the foundational parameters of the entire network stack.
Right, because when you run ipconfig all, you are essentially reading the current state of the machine's networking brain. You get the IPv4 and IPv6 addresses, obviously. You get the subnet mask, which dictates the actual size of your local broadcast domain.
Very important.
And the default gateway, which is your exit node to the rest of the world.
Right, but you also see the physical MMSE address of the network interface controller, the DNS servers you are querying, and critically, the state of the DHCP client.
Which is huge.
Let's really drill into the DHCP mechanics here, because I feel like this is where a massive percentage of local network failures actually occur.
Oh, absolutely. It's the usual suspect.
Dynamic host configuration protocol. We know it dynamically assigns IP addresses, but under the hood, this is a highly orchestrated four-step dance called the DOR-R process.
Discover, offer, request, acknowledge.
Right. When a machine boots up and it doesn't have a static IP assigned, it initiates this exact sequence.
And it does so entirely through broadcasts.
Because it doesn't know anything yet, right?
Yeah, exactly. It doesn't know who or where the DHCP server even is.
Wow.
So the client machine just sends out a DHCP discover packet. It sets the destination MMAS address to all Fs, so FFFFFFFF.
Which is a layer 2 broadcast?
Right. And it sets the destination IP to 255.255.255.255.
A layer 3 broadcast.
Exactly. It is literally shouting to the entire local subnet via UDP port 67, basically saying, hey, I'm a new MMAS address. I desperately need an IP lease.
Which means, and this is a big catch, if you have multiple VLANs in your building, that broadcast is going to hit the router interface and just die.
Yep. It drops dead.
Because routers do not forward broadcasts by default.
That is such a crucial point. If your DHCP server sits on a completely different subnet, which it usually does in an enterprise,
right,
you must configure a DHCP relay agent or an IP helper address on that router.
Could catch the shout.
Exactly. It takes that broadcast packet, converts it into a targeted unicast packet, and directly forwards it to the specific DHCP server.
So if that helper address is misconfigured by the network team,
your client is just shouting into the void.
And no server ever hears it.
Never.
Okay, but assuming the server does hear it, it sends back a DHCP offer via UDP port 68.
Right.
The client receives it, sends a DHCP request formally claiming the offered IP, and finally, the server sends a DHCP acknowledge to finalize the lease.
That's the happy path.
Right, but let's look at the failure state. Let's say the server is down, or that VLAN tagging is broken, or, port security on the switch is just blocking the request entirely.
Happens all the time.
The client shouts, waits, and gets absolutely nothing. What does the Windows OS do next?
Well, it doesn't just give up networking entirely.
It falls back to APP.
APP, automatic private IP addressing.
Yes.
You will instantly recognize this when you run ipconfig and you see an IPv4 address starting with 169.254 dot whatever.
And a subnet mask of 255.255.0.0.
Yep.
I always see engineers just roll their eyes when they spot a 169.254 address on a screen.
Oh, the heavy sigh.
Yeah, because it immediately points to a DHCP failure. But the mechanism behind APPA is actually quite clever when you think about it.
It is.
The machine isn't just like picking a random number and hoping for the best. It's actually using a defined protocol from RFC 39287 to ensure local link operability.
Right. It's a self-preservation mechanism.
Yeah.
When that DHCP timeout is reached, the Windows OS randomly generates an address within that 169.254/16 range.
Okay.
But before it actually binds that address to the network interface, it has to be absolutely sure no other isolated machine on the same switch just happened to randomly pick the exact same IP.
Because that would cause an IP conflict.
Exactly.
So it performs a gratuitous ARP?
Precisely. It broadcasts an address resolution protocol request, essentially asking, hey, does anyone on this physical network segment currently have this specific 169.254 address I just generated?
And if it hears silence in response?
It assumes the address is safe and assigns it to itself.
And if it does get a reply?
It just generates a new random address and tries the whole gratuitous ARP process again.
That's fascinating. And the practical result of this is that if an entire office building loses its main DHCP server,
Chaos.
total chaos, but every single Windows machine in that building will eventually assign itself an APPA address.
Right.
And because they are all automatically on that same 169.254/16 subnet, they can actually all still communicate with each other locally via the switch.
Yes, you can still share files peer-to-peer.
You can still print to a local network printer, assuming it also fell back to APPA.
Exactly.
But you absolutely cannot route traffic to the internet.
No, because APPA intentionally does not assign a default gateway. It's strictly local.
So when you are standing over that stressed out user's shoulder and you run ipconfig, the mere presence of a 169.254 address instantly eliminates the ISP, the firewall, the DNS servers, and the web browser from your troubleshooting scope.
It's a massive time saver.
It is. The problem is entirely localized to the DHCP lease acquisition process.
Which brings us to the actual remediation commands. ipconfig release and ipconfig renew.
The magic reset buttons.
Well, people treat them like magic reset buttons, but they actually trigger very specific packet behaviors.
Right. Let's break that down. When you type release, your machine sends a unicast DHCP release message directly to the DHCP server that originally granted the lease.
Right. It knows who gave it the IP.
Yeah, so it's explicitly returning the IP address to the server's available pool. Your interface just goes dark.
It voluntarily drops off the network.
Then, renew forces the machine to restart that entire DORA broadcast process from scratch.
And this is vital to understand because DHCP leases have timers.
Right, they don't last forever.
Typically, a client will automatically attempt to renew its lease when 50% of the lease time has expired. That's called the T1 timer.
Okay.
If that fails for some reason, it tries again at 87.5%, the T2 timer.
Wow, getting down to the wire.
Exactly. Sometimes a machine gets stuck in this weird zombie state where it thinks it has a valid lease, but the actual DHCP server has purged that lease from its database.
Maybe due to a server crash or a migration?
Yeah, exactly. The client and server just become completely desynchronized.
So forcing a release and renew literally tears down that broken state and builds a fresh, mathematically verified TCP/IP configuration from the ground up.
It's the only way to be sure.
We also have ipconfig flushdins, which clears the local DNS resolver cache, and we will definitely get deep into the DNS architecture a bit later.
Oh, DNS is a whole other beast.
Truly. But before we leave this local identity phase, we should probably mention the hostname command. It seems so trivial, right? It literally just prints the computer's name on the screen. But in a large Active Directory environment, it's a critical sanity check.
It really is. If you're managing a fleet of, say, 5,000 virtual desktops, IP addresses are totally ephemeral.
They change constantly.
Constantly. The hostname is your only real anchor. If you are remotely troubleshooting a machine, running hostname first ensures you haven't accidentally opened a reverse shell into, a production database server when you thought you were on a test client.
Oh man, that would be a resume-generating event.
It prevents catastrophic human error. Always check the hostname.
Okay, so step 1 is complete. We've verified our local configuration.
We exist.
Yes, we have a valid IP address that isn't APA. We have a subnet mask. We have a gateway. We exist on the network.
Right.
But existing doesn't mean we can communicate.
Exactly.
We have to verify the physical and logical pathways. We move from identity to echolocation.
I like that, echolocation. We need to test the local connectivity, and we do that with arguably the most fundamental tool in the entire TCP/IP suite,
The ping command.
the ping command. But ping is often vastly misunderstood by junior techs.
Yeah, they just think it's a generic is it on tester.
Right. It isn't just a generic connection tester. It is a highly specific utility that leverages the Internet Control Message Protocol, or ICMP.
Let's dissect ICMP because it operates really differently than standard TCP or UDP traffic.
It does?
ICMP is a network layer protocol. It doesn't even have ports.
No ports at all.
Right. So when you execute a ping, the operating system crafts this very specific ICMP type 8 packet, which is an echo request.
Okay.
It encapsulates that ICMP message directly inside an IP header, slaps on the destination IP address, frames it with MP addresses, and just puts it on the wire.
And if the target device receives that type 8 packet, and this is important if its firewall rules actually allow it,
Right, big if.
the networking stack of the target device processes it and automatically generates an ICMP type 0 packet.
An echo reply.
An echo reply, and it sends it right back to the source. The ping utility on your machine is basically just a really precise stopwatch.
If it's just tracking time.
Exactly. It records the exact microsecond the type A packet left the interface and the exact microsecond the type 0 packet returned. That difference is your round-trip time, or latency.
It's literally like a submarine pinging sonar.
That's exactly what it is.
But the architecture of how we use ping for diagnostics is highly structured. You don't just immediately ping Google when something is broken.
Never.
There is a rigid 4-step methodology to isolate the fault domain.
Right.
Step 1. Ping the loopback address, 127.0.1. Now, to a lot of people, this seems like a total waste of time.
It seems crazy.
Yeah. I mean, wait, why am I just talking to myself? What does that actually prove? The packet never even hits the copper of the network cable. It stays entirely inside the machine.
Well, the value is verifying the absolute integrity of the operating system's kernel space network stack.
Okay, unpack that.
When you ping 127.0.1, the ICMP request is generated by the user mode ping application, right?
Right.
It's passed down into the kernel to the TCP IP driver, routed to the virtual loopback interface, and then immediately handed right back up the stack to be processed as a reply.
So it bypasses the physical network interface card hardware entirely?
Entirely. Though it does rely on the driver being loaded.
Okay, so if a loopback ping fails, you don't check the switch, you don't check the Ethernet cable.
You don't even check the DHCP server.
Right. Your local TCP IP protocol suite is just fundamentally corrupted.
Exactly. You might have a severe driver conflict, maybe a corrupted registry, or catastrophic malware interfering with the kernel's ability to process networking protocols.
Wow. So you are looking at a system repair or a full OS rebuild, not a network cable swap.
It cleanly divides software failure from network failure.
Which is brilliant.
Once the loopback is verified, step 2 is pinging your own machine's assigned IPv4 address, the one you just found via ipconfig.
Now wait a second. If pinging the loopback verifies the software stack, what does pinging my own assigned IP address actually prove? Isn't it just doing the exact same thing?
It is very similar, yes, but it takes the packet one step further down the hardware abstraction layer.
Oh, okay.
When you ping your bound IP address, the packet must actually hit the network interface card driver and the physical hardware's logical bindings before turning around.
So if loopback succeeds, but pinging your own IP fails.
It indicates a hardware-level failure with the NIC itself, or a severe issue with how the OS driver is binding the protocol to that specific piece of hardware. The physical card might be disabled in the BIOS, or the driver might just be completely home.
That is a very subtle but critical distinction. Okay, step 3. Ping the default gateway.
Now we're leaving the machine.
Right. This is where the packet finally leaves your computer, travels across the physical medium, whether that's twisted pair Ethernet or Wi-Fi radio waves, hits the local router's internal interface, and hopefully returns.
And if you can successfully ping your gateway, you have definitively proven that your physical layer connection to the local network infrastructure is intact.
Your cables are good.
Your cables are good, your switch is forwarding frames correctly, and your subnet configuration is perfectly accurate. You have full local network operability.
And finally, step 4. Ping a remote host across the internet.
Like a public DNS server.
Yeah, like 8.8.8 or at 8.8 or 1.1.1.1. This forces the packet to be routed by the default gateway out of the local network, across the ISP infrastructure, and out into the broader internet.
And this step-by-step isolation is so powerful because it actively stops you from chasing ghosts.
Yes.
But to really wield ping effectively, you have to know how to read the failure messages.
Because they aren't all the same.
No, the command prompt provides highly specific diagnostics if you actually understand the terminology.
Let's look at the first failure state. Destination host unreachable. This is a fascinating error because it usually includes an IP address right before the message.
Right, it'll say, reply from your IP, destination host unreachable.
The key here is that the reply is coming from your own machine.
Yes, your computer is generating the error, not the network.
Why?
Well, when you try to ping an address, your machine looks at its local routing table.
Okay.
If the destination IP is on the same local subnet, your machine sends an ARP request to find the target's MAC address.
Right, address resolution protocol.
Exactly. If the target doesn't respond to that ARP request, maybe it's physically powered off or the IP is currently unassigned, your machine just gives up.
And it generates this destination host unreachable error.
Right. It essentially means, look, I know this device should be right here next to me on the switch, but I absolutely cannot find its physical hardware address.
But what if the error says, reply from gateway IP destination host unreachable?
Ah, now the error is being generated by the router.
Okay.
Your machine successfully sent the packet to the default gateway. The router accepted it, looked at its own routing table, and suddenly realized it has no valid route to forward the packet any further.
So it just drops it.
It drops the packet and sends an ICMP Type 3 packet destination unreachable back to your machine.
So this implies a routing protocol failure on the infrastructure side?
Exactly. The router has literally lost its map.
Contrast both of those with the classic request timed out.
A timeout is entirely different.
How so?
A timeout means the ICMP echo request packet successfully left your machine, successfully navigated all the routing tables, and went out into the void.
Okay.
But the timer on your ping application hit its limit, which is usually 4,000 milliseconds, or 4 seconds, and no echo reply ever returned.
And a timeout can be caused by several factors, right? I mean, it could be severe network congestion causing the packet to be dropped by an overwhelmed router queue.
Absolutely.
But it could also mean the destination host received the packet perfectly fine, but is intentionally configured to drop ICMP traffic.
Which is incredibly common nowadays for security reasons.
Yeah, to prevent network discovery scanning.
Exactly. Many corporate firewalls just silently drop ICMP Type 8. The host is there, it just completely refuses to acknowledge you.
Which is why relying solely on ping to verify if a server is online is a fundamentally flawed strategy.
Totally flawed.
If a web server drops ICMP traffic, your ping will time out, but you might still be able to connect to its website on TCP port 443 perfectly fine.
You'll see this all the time.
Now, there is one switch for ping that I think is indispensable for intermittent troubleshooting, and that's the HUST switch.
Oh, PingTIA, a lifesaver.
Yeah, ping target.
Yeah.
Normally, Windows just sends 4 packets and stops. The HUST switch turns it into an infinite loop.
Right. It will send a packet every single second until you force a keyboard interrupt with Ctrl plus C.
It's the ultimate circuit continuity tester.
It really is.
Mm-hmm.
I mean, if a user complains that their connection drops randomly during, like, Zoom video calls, a standard 4-packet ping will likely succeed and tell you absolutely nothing.
Because it only tests 4 seconds of time.
Exactly.
Yeah.
But if you run ping T to the gateway and just let it run for 10 minutes, you might suddenly see a pattern.
Like 50 successful replies, then 3 timeouts, then 50 replies.
Yes. You are identifying transient packet loss. I've personally used this to find everything from bad switch ports to, I kid you not, Ethernet cables that were being crushed by a user rolling their desk chair over them.
Oh, wow. Really?
Yeah. The intermittent drop only happened when physical pressure was applied to the cable by the wheels of the chair.
That's hilarious, but it proves the point. The continuous data stream reveals the physical reality.
It does.
So we've used ping to prove that our local gateway is reachable, but what if step 4 fails?
The internet test.
Right. What if we ping 8.8.8.8 and it times out, but the gateway is perfectly fine? We know the packet is leaving our network, but we have literally no idea where it is dying in the wilderness of the internet.
Because ping is too binary.
Exactly. It just says yes or no. We need to map the exact geographical routing path.
Which transitions us perfectly from simple echolocation to network cartography.
I love that term.
We have to map the transit hops, and we do that using the tracert command in Windows.
Or traceroute in Linux environments.
Right.
Now, tracert is a brilliant piece of engineering because it isn't actually a new protocol at all.
No, not at all.
It's an ingenious exploitation of a specific field within the standard IP packet header, the time to live, or TTL field.
Let's explain how the TTL field works normally first, because understanding the baseline is critical to understanding how traceroute hacks it.
Okay, go for it.
When any IKEY packet is generated, the operating system assigns it a TTL value, usually 64, 128, or 255.
Okay.
This value is a built-in safeguard against routing loops. If a routing table somehow gets corrupted, a packet could theoretically bounce between 2 routers infinitely.
Which would eventually cause a broadcast storm or completely saturate the link.
Exactly. It would take down the internet.
Right.
So to prevent this, every single time a router receives a packet and forwards it to the next hop, it is mandated by the IP protocol to decrement the TTL value by exactly 1.
So it starts at 128, router A drops it to 127, router B drops it to 126.
Exactly. And if that TTL value ever reaches 0,
the router currently holding the packet is required to discard it entirely.
but it doesn't just silently drop it into the void. The router generates an ICMP Type 11 message time exceeded and sends it all the way back to the original source IP to inform them that the packet basically died of old age in transit.
And this is where tracert performs its absolute magic.
It's so clever.
It weaponizes that time-exceeded mechanism. When you run tracert, it wants to find the first router in the path, right? So it intentionally crafts an ICMP echo request packet, but it maliciously sets the TTL field to exactly 1.
So sneaky. It puts the packet on the wire. The packet hits your local default gateway, which is the very first hop.
Right.
The router receives it, processes it, and decrements the TTL from 1 to 0.
The packet is now invalid.
Yep. The router drops the ICMP echo request and generates that ICMP time exceeded message, sending it right back to your computer.
The tracer application receives that time exceeded message, looks at the source IP of the message, and says, aha, I now know the IP address of hop 1.
It records the latency, prints it on your screen, and then crafts the second packet.
But this time, it sets the TTL to 2.
Right. The packet hits hop 1, TTL drops to 1, and it is safely forwarded.
It hits hop 2, TTL drops to 0.
Hop 2 discards it and sends back a time-exceeded message. The tracer app records the IP of hop 2.
It then sends a packet with TTL3, then TTL4, systematically discovering every single router in the path until the TTL is finally large enough that the packet actually reaches the destination.
Which then responds with a standard echo reply instead of a time exceeded.
It's an incredibly elegant diagnostic tool. I mean, it's like tracking a package through various postal sorting facilities. You can literally watch the packet leave your local network, hit the ISP's local edge router, travel to a regional peering exchange.
Cross an autonomous system boundary.
Yeah, and dive into a massive data center backbone. And what we are looking for in that output is the exact hop where things go wrong.
The broken bridge.
Right. If hops 1 through 6 show a steady 20 milliseconds of latency, but hop 7 shows asterisks, which indicate timeouts, you have found the specific IP address of the router where the bridge is out.
This is a huge, but you have to interpret tracer data with extreme caution.
Because it can lie to you.
It absolutely can lie to you, usually due to something called control plane policing, or CoPPA.
Explain that.
So enterprise routers essentially have 2 planes. The data plane, which forwards regular traffic via hardware ASICs at line rate, and the control plane, which is the actual CPU of the router processing routing protocols and generating things like ICMP messages.
And generating those ICMP time-exceeded messages takes valuable CPU cycles.
Exactly. And network administrators aggressively protect their router CPUs.
Makes sense.
They will configure CoPP to heavily deprioritize or completely drop ICMP generation if the router is busy doing actual, routing work.
So you might run a tracer and see hop 6 return 3 asterisks timeouts, but hop 7 and hop 8 respond perfectly fine.
Yes. A lot of junior engineers will see those asterisks at hop 6 and just start screaming, packet loss, that router is dropping packets, the ISP is down.
But if it were truly dropping beta packets, hops 7 and 8 could never be reached in the first place.
Exactly. The data plane is forwarding the traffic perfectly fine. Hop 6 is just programmed to ignore your ICMP request to save its CPU.
Right.
You have to analyze the entire route comprehensively, not just look for single asterisks and panic.
Yeah. And tracert is just a quick snapshot, too. It only sends 3 packets per hop. If you have an intermittent latency issue, say a peering link that is only congested for, 2 seconds every minute, tracert will likely completely miss it.
It's too fast.
Which is why the advanced toolset includes pathping.
Oh, pathping. It is the heavy-duty, statistical big brother to tracert.
Yes, it is.
It perfectly merges the geographic discovery of traceroute with the endurance testing of ping-t.
So when you execute a pathping, it begins by mapping the entire route, discovering all the hops just like tracert does.
Right, but then it stops and prepares for an endurance run.
It initiates this massive 200-second barrage.
By default, it sends 100 ping requests to every single hop along the entire discovered path simultaneously.
Wow.
It waits over 3 minutes, collecting all this data, and then compute a highly detailed statistical matrix.
It doesn't just show you latency.
No, it shows you the exact percentage of packets lost at each specific node.
So if a core switch in a provider's network has a failing memory buffer and is randomly dropping, say, 2% of the packets passing through it, tracert will almost certainly miss it.
But pathping will highlight that 2% packet loss directly on that specific hop's IP address.
It gives you the undeniable statistical proof you need to actually open a ticket with an ISP and escalate an infrastructure problem.
You can't argue with the math.
But it requires patience. I mean, staring at a blinking cursor for 200 seconds feels like an absolute eternity when a system is down and users are actively yelling at you.
Oh, it feels like an hour. But the analytical depth of the data it returns is completely unmatched for identifying transient route degradation.
Okay, so let's reset our scenario for a second. We verified our local IP with ipconfig.
Okay.
We tested local connectivity with ping.
Sure.
We traced the route out to the internet, and the tracert to 8.8.8.8 is totally clean. The packet is making it to the destination and back.
So the network layer 3 is functioning flawlessly.
Flawlessly. But the user still cannot open www.google.com in their web browser. The internet is still, quote-unquote, down.
Ah. So the network is healthy, but the naming directory is broken.
We have entered the realm of name resolution troubleshooting.
The human-readable abstraction has failed.
Because humans cannot navigate the modern internet using IP addresses. I mean, nobody memorizes strings of numbers to check their email.
No, we rely on the domain name system, DNS, to instantly translate human-readable host names into machine-readable IP addresses.
And if that translation fails, the internet is functionally inaccessible to the user, even if the routing infrastructure is totally perfect. It's exactly like having the exact GPS coordinates to a specific building in a massive city, but all the street signs and business names have been completely removed.
That's a great way to put it.
You can physically drive to the latitude and longitude, but you have literally no idea what the building is called or what's inside it.
To diagnose this, we have to really look at the DNS resolution process, which actually involves multiple layers of caching and querying.
Right. When you type a URL into a browser, your computer doesn't just immediately query a DNS server on the internet.
No, it checks its own local DNS resolver cache first.
To save time.
Exactly. The OS remembers recent lookups to save time and bandwidth. If you visited a site 5 minutes ago, the IP address is likely still in your local cache, dictated by a time to live, or TTL, value set by the domain owner.
And this local cache can become a massive liability, right?
Oh, absolutely.
If a website changes its IP address, maybe they, failed over to a backup data center, your computer might stubbornly hold on to the old invalid IP address until the TTL expires.
You try to load the site, your cache provides the old IP, and you get a connection timeout.
Even though the rest of the world can see the site perfectly fine.
This is exactly why ipconfig flush DNS is such a common standard remediation step.
It forces the operating system to completely purge its local resolver cache.
It deletes the positive entries, the successful lookups.
And critically, it deletes the negative cache entries.
Negative caching is so important to understand.
Yeah, explain that.
If you mistype a URL, the DNS server tells your computer, hey, that domain does not exist.
Right.
Your OS will actually cache that negative response for a short time, so it doesn't have to keep repeatedly asking the server about a fake domain if you keep clicking reload.
So flushing the cache clears all of those assumptions and forces the machine to actually ask the network for a fresh resolution. But what if flushing the cache doesn't work? We need to figure out why the DNS query itself is failing.
And for that, we use the nslookup command, name server lookup.
This command is like a scalpel because it completely bypasses the Windows OS resolver cache.
Yes, it acts as an independent DNS client, crafting a raw query and sending it directly to the DNS server via UDP port 53.
When you type nslookup google.com, the tool sends the query and prints out two critical pieces of information on your screen.
First, it tells you exactly which DNS server it just asked.
Which is usually the server assigned to you via DHCP, like your ISP's recursive resolver, or maybe your corporate domain controller.
Right. And second, it shows you the IP address the server returned.
If nslookup returns an IP address instantly, but your web browser still can't load the page, you have just isolated the problem completely away from the network.
Your DNS server is working perfectly.
The problem resides in the local application layer. Maybe a browser extension is blocking the connection, or a local proxy setting got misconfigured.
Conversely, if nslookup returns a timeout, you know the query is dying in transit. The DNS server is unreachable.
But nslookup allows you to pivot and change the query destination dynamically, right?
It does. You can just type server 8.8.8.8 to force nslookup to send its very next query to Google's public DNS servers instead of your local ISP server.
And this is huge. If the query to your local server times out, but the query to 8.8.8.8 succeeds and returns an IP, you have successfully proven that your network routing is fine, your firewall is allowing outbound port 53 traffic.
But your specific local DNS server has crashed, or its database is corrupted.
The fix is literally simply updating your DHCP scope to hand out a different functioning DNS server.
And we really must mention here that DNS operates on both UDP and TCP port 53.
Right, it's not just UDP.
Standard small queries use UDP because it is
connectionless, and extremely fast.
But if a DNS response is larger than 512 bytes, which is increasingly common with the addition of DNSCC cryptographic signatures,
Or if the server is performing a full zone transfer.
the protocol automatically falls back to TCP port 53 to ensure reliable delivery of the much larger payload.
And a very common misconfiguration is network administrators blocking TCP port 53 on their firewalls, thinking DNS is purely UDP.
Which causes bizarre intermittent resolution failures for complex domains.
nslookup is also a powerful tool for diagnosing broader infrastructure issues using specific record types.
Yeah, by default, it queries for A records, which map a name to an IPv4 address. But you can change the behavior by typing set type MX.
MX stands for mail exchange.
These are the DNS records that tell the global internet which servers handle email for a specific domain.
Right. If a company suddenly stops receiving all external emails, a systems administrator won't just blindly check the local exchange server first.
They will run nslookup with set type MX against their own domain.
Exactly. If the query returns nothing or points to an invalid IP address, they know immediately their DNS zone file has been altered or corrupted.
The internet literally doesn't know where to deliver their mail.
You can also use settype.txt to investigate SBF records for email security.
Or set type SRV to find Active Directory domain controllers. DNS is definitely not just a phone book. It is a highly structured, distributed database that controls the routing logic for entire application ecosystems. Okay, let's step back and look at the architectural map we've traversed so far.
It's been a journey.
We verified our local network interface with ipconfig. We tested the kernel stack and physical gateway with ping. We mapped the geographic routing latency with tracert and pathping.
We bypassed the local cache and verified the directory services with nslookup.
Right. So we have successfully routed our packet across the world to the exact correct IP address. We are standing right in front of the destination server.
But now we have to look at the application layer.
Exactly. Which doors on this server are actually open? And more critically for our local machine, what connections are silently active in the background?
We are shifting our focus from the network transit pathways to the endpoints themselves.
We need to investigate the transport layer protocols, TCP and UDP.
And we do that using netstat network statistics.
Now, netstat can be a really intimidating command.
Oh, it's terrifying the first time you see it.
Yeah. When you execute it, you are presented with this rapidly scrolling wall of text, displaying local addresses, foreign addresses, and states like listening, established, time wait, and close wait.
To even understand this output, we have to briefly discuss the TCP three-way handshake.
Okay, let's do it.
Transmission Control Protocol is connection-oriented. Before any data can be transmitted, a formal connection must be securely established. The client sends a SYN packet, a synchronized request, to a specific port on the server.
The server, if it is actually listening on that port, replies with the SYN ACK packet.
The client then acknowledges receipt with an ACK packet.
The connection is now established, data can finally flow.
And when they are done, they send affine packets to tear down the connection.
Netstat is essentially giving you a real-time view into the state machine of every single TCP connection on your operating system.
Exactly. If you run a web server, it should theoretically have a process bound to TCP port 80 for HTTP and TCP port 443 for HTTPS.
When you run netstat A, which shows all active connections and listening ports, you scan that massive list.
And if you do not see 0.0.443 in a listening state, your web server software is not running.
The door is closed. No amount of network troubleshooting will fix it because the application itself has failed to bind to the socket.
It is the ultimate service verification tool.
Email uses port 25 for SMTP. SMB file sharing uses port 445.
If a service is supposed to be running, netstat will prove whether it is actually awake and listening for incoming packets.
But in a modern environment, running just netstat A by itself is almost useless.
Completely useless.
Right, because an average workstation might have literally hundreds of active connections to various cloud services, update servers, and background telemetry.
Just seeing that port 50509 is established to some random IP address doesn't give you any actionable intelligence.
This is why the weak B switch is paramount. Netstat DAS-B.
The Match B switch elevates netstat from a simple diagnostic tool to a potent security auditing mechanism.
It stands for binary or executable.
Yes, when you run netstat DAP-B, you must do it from an elevated administrator command prompt.
Why is that?
because you are asking the OS kernel to map the active network socket directly to the process ID, the PID, and the actual executable file on the hard drive that opened it.
So instead of just seeing an active connection to an IP, the output will explicitly tell you that chrome.exe is responsible for the connection on port 44T3.
Which is expected behavior.
But if you run netstat-b and you see a connection established on a bizarre high port, like 4444,
And the executable attached to it is svchos.exe, running out of a user's temporary app data folder instead of this system32 directory.
you have just detected a compromise.
The material refers to this as malware beaconing.
Right. When a machine is infected with a remote access Trojan, or ransomware, it needs to communicate with its command and control server.
But modern firewalls block incoming connections.
So the malware uses a reverse shell.
Exactly. It initiates an outbound connection from the infected machine to the hacker server, completely bypassing the inbound firewall rules.
And netstat-b allows you to see those outbound beacons in real time and identify the specific malicious executable driving the connection.
It is hands down the easiest way to catch a piece of malware silently calling home.
There's a really important performance tip when running this command, though.
Yes, the end switch.
Right. Netstat tries to be helpful by performing reverse DNS lookups on every single foreign IP address it finds, trying to show you host names instead of raw IP numbers.
And if you have hundreds of connections and the DNS server is slow or unresponsive,
Netstat will appear to just hang for minutes.
to prevent that, you always append the land and switch.
Netstat-n forces the tool to display addresses and ports in numerical format only.
It skips the DNS resolution entirely, dumping the raw socket data instantly,
Most engineers will just combine the switches. Netstat-nb.
giving you all active ports, numeric addresses, and the associated executables delivered immediately.
We also have the statistical switches, E for Ethernet interface statistics and NS for protocol-specific statistics.
Right. If you suspect low-level packet corruption, Netstat-NS will show you the exact number of TCP segments retransmitted.
Or UDP packets received with errors.
Okay.
It provides a highly granular view into the health of the transport layer. Now, this analysis of ports and services provides a perfect transition to our next major architectural block.
Remote access.
Let's say we used netstat on a server and verified that TCP port 3389 is in a listening state. Port 3389 is the default gateway for one of the most powerful and dangerous protocols in the Windows ecosystem.
Remote desktop protocol.
We are moving into remote access technologies.
Because finding the server and verifying the network path is really only half the battle.
Exactly. Systems administration requires the ability to physically take control of a distant machine over those pathways.
Remote access is the mechanism that allows a centralized IT team to manage a globally distributed infrastructure.
In the Windows environment, the native graphical tool is Remote Desktop Connection, which runs on the executable mstsc.exe Microsoft Terminal Services Client.
It utilizes RDP over TCP
Yeah.
and increasingly UDP, port 3389.
And it is vital to understand that RDP is not just some cheap screen scraping tool that sends pictures of a desktop back and forth.
No, it is a highly sophisticated display protocol that uses virtual channels and drawing primitives.
Explain that, because I think a lot of people assume it's just a video stream.
When you connect via RDP, the server isn't just taking a video of its screen and streaming it to you. That would consume massive bandwidth.
Right.
Instead, the RDP protocol actually intercepts the graphic device interface, the GDI commands.
The instructions the OS uses to draw windows, text, and menus.
Yes. And it transmits those mathematical instructions over the network. Your local client receives the instructions and renders the graphics locally.
Which makes RDP incredibly responsive, even over really high latency WAN links.
And it supports extensive local resource redirection.
Yeah. If you copy a block of text or a file on your local machine, the RDP clipboard redirection virtual channel allows you to paste it directly onto the remote server's desktop.
Or if you hit print on a document hosted on the remote server, printer redirection tunnels that print job back through the RDP session to the physical printer sitting on your desk.
It creates a totally seamless integration of remote compute and local hardware.
But there's a fundamental operational architecture to RDP that dictates how it must be used.
Right, it's not for everything.
RDP provides an exclusive, isolated desktop session.
Meaning?
For standard Windows client operating systems like Windows 10 or 11, only one interactive graphical session can exist at a single time.
So if a user is physically sitting at a desk working on a machine, and an administrator initiates an RDP connection to that machine in the background,
The physical user is immediately locked out.
Their screen goes straight to the login prompt, and their session is suspended.
You literally commandeer the console entirely, which is perfect for server administration, obviously.
Right. If a server is sitting headless in a freezing data center rack, nobody is sitting at the physical monitor anyway.
You RDP in, do your work, and log out.
But this exclusive session architecture makes standard RDP completely inappropriate for help desk support.
Oh, yeah. If a user calls you because they don't know how to format a pivot table in Excel, and you RDP into their machine to show them,
You kick them out of their own session. They can't see what you are doing at all.
you fix the spreadsheet, log out, they log back in, and they still haven't learned how to do it.
This is exactly why Microsoft built a parallel technology into the OS, Microsoft Remote Assistance, or MSRA.
And remote assistance operates on entirely different principles.
First, it is an invitation-based protocol. An administrator cannot just silently connect and take over.
The user sitting at the machine must generate an invitation file or use an integration with a chat client to actively request help and provide a password.
And second, and most critically, Remote Assistance utilizes a technology called session shadowing.
Meaning it doesn't create a new isolated desktop session.
Exactly. It attaches to the existing interactive session. It mirrors the display output.
So both the user and the administrator see the exact same screen simultaneously.
The user can watch the administrator's mouse move, see exactly where they click, and observe the troubleshooting process.
They share control of the keyboard and mouse. It is a collaborative educational tool, whereas RDP is strictly an administrative takeover tool.
Now, the source material also outlines alternative remote access architectures because graphical desktops are incredibly resource-intensive.
Right. If you need to restart a service on 100 servers, opening 100 RDP windows is just impossible.
This is where WinRM Windows Remote Management comes in.
WinRM is the backbone of modern, scalable Windows administration.
It is a command line interface that utilizes the WS Management Protocol, transmitting SOP-based XML messages over standard HTTP or HTTPS ports.
TCP 5985 and 5986, which makes it incredibly firewall-friendly.
Yes. It allows administrators to execute PowerShell scripts on remote machines without ever loading a heavy graphical interface.
It uses a fraction of the bandwidth and processing power of RDP.
You can run a script that leverages WinRM to query the event logs of 1,000 servers simultaneously, aggregate the data, and return a report in seconds.
And for the Linux and Unix ecosystems, the equivalent standard is Secure Shell, or SSH.
SSH operates on TCP port 22 and provides a secure, encrypted terminal session.
It relies heavily on public key cryptography rather than simple passwords, making it highly resistant to brute force attacks.
And importantly, Microsoft has fully embraced SSH, integrating a native open SSH client and server directly into modern builds of Windows.
The material also briefly mentions SpiceCC, the simple protocol for independent computing environments.
This is a highly specialized protocol designed primarily for virtual desktop infrastructure, or VDI.
How does SpiceE differ from RDP fundamentally?
Well, RDP was originally designed for physical hardware. Spice is built from the ground up specifically for hypervisors, like KVM. It uses para-virtualized QXL graphic drivers to communicate directly with the hypervisor's virtual hardware, providing highly optimized rendering for virtual machines.
Particularly for multimedia and multi-monitor setups, it's a hypervisor-native approach to remote display. Okay, we have to address the elephant in the room.
Let's do it.
We just spent this entire deep dive establishing how to ensure network connectivity, how to map the routing paths, and how to utilize incredibly powerful protocols like RDP and WinRM to take absolute administrative control over a machine from anywhere on the planet.
It's a lot of power.
From a security perspective, this sounds like a nightmare. If TCP port 3389 is explicitly designed to hand over control of the OS, leaving it exposed on the internet is an invitation to disaster.
It is not just an invitation. It is an absolute guarantee of compromise.
Yeah.
The threat landscape surrounding RDP is severe. Automated botnets continuously scan the entire IPv4 address space looking for open 3389 ports.
If you place a server on the public internet with RDP exposed, it will be discovered and attacked within minutes. We saw this with vulnerabilities like Bluekeep, which allowed remote code execution pre-authentication.
Terrifying. But even without zero-day vulnerabilities, the primary attack vector is just simple brute force.
The bots will initiate thousands of login attempts per hour, utilizing massive dictionaries of compromised passwords, trying to guess their way into the administrator account.
And because RDP provides full graphical access, once an attacker guesses the password, they essentially have physical access to the machine.
They will disable the antivirus, exfiltrate data, and deploy ransomware across the entire local network. So how do we mitigate this? How do we fortify the castle while still allowing remote administration?
The first layer of defense built into the protocol itself is network-level authentication, or NLA.
Historically, the RDP architecture was flawed, right?
Very flawed. When a client connected to port 3389, the server would immediately spin up a session, render the graphical Windows login screen, and transmit it to the client.
The client would then type in their password. That seems fine on the surface.
But spinning up that graphical session consumes RAM and CPU on the server.
Ah.
An attacker could initiate thousands of simultaneous connections without ever entering a password, exhausting the server's resources and causing a denial of service.
And it exposed the operating system's graphical subsystem to potential exploits before the user was even verified. So NLA flips the sequence.
Exactly. NLA utilizes the CRED SSP protocol to force the authentication handshake to occur at the network layer before a full graphical session is ever established.
So the client must cryptographically prove they possess valid credentials via a secure channel first.
If the credentials are invalid, the server drops a connection immediately, spending almost zero computational resources.
It stops brute force scripts and denial of service attacks dead at the perimeter.
The material also emphasizes standard credential hygiene, of course. Complex passwords, account lockout policies to stop brute forcing, and enforcing multi-factor authentication via Radius or cloud identity providers.
Because if a user has a weak password and no MFA, even NLA cannot protect the system. It will happily authenticate a valid stolen credential.
But the absolute gold standard, the architectural imperative for remote access, is network isolation.
You never, under any circumstances, expose RDP or WinRM directly to the public internet.
Never. You restrict those ports to the local area network only, or you mandate that remote users encapsulate their traffic within a virtual private network.
VPNs, this is really the synthesis of everything we've discussed today. The raw network protocols, IP, ICMP, TCP, provide connectivity. They are the public highways.
And anyone can intercept packets on a public highway and read the unencrypted payloads.
A VPN takes that raw connectivity and wraps it in cryptographic armor.
A VPN establishes an encrypted tunnel between the remote client and the corporate firewall. It provides three critical security pillars.
Okay, let's hear them.
First, confidentiality. The payload of the packet is encrypted, meaning if an attacker intercepts the traffic at a public coffee shop, they see only scrambled ciphertext.
They cannot see the RDP keystrokes or the file transfers.
Right. Second, integrity.
Integrity ensures the packets have not been maliciously altered in transit, right?
Yes. The VPN uses cryptographic hashing. If a single bit of the packet is slipped by a man in the middle, the hash fails and the packet is discarded immediately.
And third, authentication. The VPN verifies the exact identity of the user and the device before ever allowing them onto the network.
Once the VPN tunnel is established and the user is authenticated, the remote machine is essentially assigned an internal IP address.
They are virtually placed onto the corporate LAN.
And because they are now logically inside the trusted perimeter, they can safely initiate an RDP connection to an internal server.
Because that server's port 3389 is securely shielded from the outside world by the edge firewall?
Exactly. Our sources detail several VPN protocols used to build these tunnels, and they operate at different layers of the OSI model.
The legacy protocol is PPTP, point-to-point tunneling protocol, which is largely considered completely obsolete now due to fundamental cryptographic flaws in its authentication mechanisms.
Right. For deep infrastructure site-to-site VPNs, where you are connecting two physical office buildings together permanently over the internet, administrators rely heavily on IPsec, IP security.
IPsec is incredibly robust because it operates at the network layer, layer 3. It doesn't just encrypt the payload, it can actually encrypt the entire IP packet.
IPsec uses a really complex architecture. It uses IKE, the Internet Key Exchange, to negotiate the cryptographic algorithms and establish the secure tunnel phases.
Then it uses ESP, the encapsulating security payload, to actually encrypt the data flowing through the tunnel.
It can operate in transport mode, which encrypts only the payload, or tunnel mode, which encrypts the original IP header as well, entirely hiding the internal routing structure from the public internet.
It is highly secure, but complex to configure, and often struggles with NAT traversal if not configured very carefully.
Which is why for remote workers, the road warriors sitting in hotels or airports, the industry has largely shifted to SSL TLS-based VPNs.
TLS VPNs operate higher up the stack, at the transport and application layers. They utilize the exact same transport layer security cryptography that secures HTTPS banking websites.
Because it uses standard TLS, usually over TCP port 443, it passes through almost any public firewall seamlessly.
You don't have to worry about NAT traversal or complex IKE phase negotiations suddenly failing on a hotel Wi-Fi network.
The user often just opens a web browser, logs into a portal with MFA, and the VPN client tunnel is established automatically.
It provides exceptional security with vastly simplified deployment.
Knowledge of these diagnostic paths is really only valuable when applied within a secure architecture.
If you know how to trace a route and open a port, but you don't understand the cryptographic necessity of a VPN, you aren't an administrator. You are just building very efficient, unarmored roads for threat actors to exploit.
Security and connectivity are inextricably linked. You simply cannot troubleshoot one without understanding the boundaries imposed by the other.
We have covered a massive architectural landscape today. Let's trace the journey of our packet one final time.
From the top.
We started at the local interface, utilizing ipconfig to verify our DHCP door process and ensure we weren't isolated by an APA address.
We used ping to generate ICMP Type 8 echo requests, testing the integrity of our OS kernel stack via the loopback, and verifying physical layer forwarding to our default gateway.
When binary connectivity wasn't enough, we manipulated the IP header TTL field, using tracert to force ICMP time-exceeded messages, mapping the geographic router hops.
We endured the 200-second statistical barrage of pathping to identify transient node degradation.
We bypassed the OS resolver cache with nslookup, directly querying UDP port 53 to isolate DNS resolution failures from network routing failures.
We analyzed the TCP state machine, using netstat.mip, mapping listening ports to executable processes to hunt for malware beacons.
And finally, we leveraged the virtual channels of RDP and the session shadowing of remote assistance to physically command remote infrastructure.
All while ensuring those protocols were heavily encapsulated within the cryptographic integrity of an IPsec or TLS VPN tunnel.
It is a complete, structured diagnostic methodology. When a user complains that the network is down, you are no longer relying on a lying graphical icon.
You have the theoretical knowledge and the specific command line tools to interrogate every single layer of the OSI model.
Isolate the fault domain and prove definitively whether the failure is hardware, software, routing, or directory services.
If we look at the trajectory of the industry, however, it does raise a pretty profound question. We are rapidly moving toward an era of software-defined networking and heavily automated AI-driven infrastructure.
That's true.
Modern SD-WAN controllers can instantly sense a drop in link quality, dynamically run automated path pings in the background, recalculate BGP routes, and shift traffic before a user even notices the latency.
Endpoint detection and response systems are dynamically reading netstat data, utilizing machine learning, to instantly kill executables that attempt unauthorized outbound connections.
The network is literally becoming self-healing.
It is an incredible evolution of capability.
It is. But it begs the question, as these systems become more abstracted, more autonomous, and more visually complex on the management dashboards,
Will the raw underlying knowledge of ICMP types, TTL fields, and TCP handshakes become a lost art?
will the command line become an ancient language? Or will there always be an inevitable moment when the automation loops fail, when the AI hallucinates a routing policy and the dashboard goes entirely dark, that there is an absolute undeniable need for a human engineer to open a terminal, bypass the abstraction, and manually ask the machine, where are you trying to go?
A human element rooted in the fundamental physics of the protocol layer. I personally believe that need will never disappear. The tools may change, but the architecture remains. We will leave you with that thought to ponder. Thank you for joining us on this deep dive into the underlying mechanics of network troubleshooting and remote access architecture. Our goal is to ensure you possess the depth of knowledge required to be the most capable engineer in the room. Keep interrogating the systems, trust the packets over the GUI, and we will see you on the next deep dive.